I'll be talking about how to build reflection C++. But I want to start out with a little bit of story time. Imagine you're writing a C++ program, which probably many of you do, and you have a struct in your program, and you want to send that struct over the network. So wouldn't it be great if we could take this struct, put it into a function, and get a JSON string out of that? Something similar to this. What we have here is a simple struct called user. The struct has three members: an ID, a name, and pets, which is a vector of string. Next, we just create an instance of the user. We give him the ID 42. We give him his name. He's called John. And his two cute dogs, Buddy and Cooper. Next, we just call the JSON colon stringify function. This stringify function will return one string. And that's the JSON representation of the class we just plugged in. It looks similar to this, or it will actually look exactly like this. It's a pretty much standard JSON object. It can be passed around, can be sent over the network, can be serialized to disk, and can be unserialized again as well. So let's take a look how we do this. I mean, there's a pretty simple way, right, to do that. We can just create an overload for each type of the structs we have. So we create an overload like this, which will look like this for the user. We create a new JSON serializer. We will serialize the int. We will serialize the string. We'll start a new array. And then we will serialize everything to string and return from the function. This is pretty simple. Probably many of you have done that before. It's pretty cool. We have now a JSON string. But if we take a deeper look at that, we will see that this can create bugs. Because if we imagine we have a large class, a lot larger than the user struct here, has like 20 members or even more. And one day, a team member comes along, you don't know, from another team. You've created the class 6 months ago. And you will add a new member. But he doesn't know about that function. So he forgets to add a serialization call in that function. Now you'll get the JSON, you'll pass it to some endpoint, and you will get a response back. And you're wondering, why is that response wrong? We have everything in the class. What's missing? So we can see here, obviously, it creates like some terrible bugs. We'll get out of sync quickly. And there must surely be a better way. I think we can find a better way in some other languages. Herb, earlier today, showed some C#. And I will also show some C#. We create pretty much the same program as we did in C++. We create a user, has an ID, has a name, and a vector of strings, which in C# is a list. And we need to initialize it as well. Then we create an instance. We set the ID to 42 again. He's called John, and he has two very cute dogs, Buddy and Cooper. Then we call a function, JSON convert, serialize object, and that will give us back a string. There's one minor difference to the C++ source code. And the difference is, this is all the code we need. There's nothing more to it. You can take that snippet of code, put it into the source editor with C#, correct the includes, the imports, run it, and print a JSON string. Nothing more required. How does that work? It's pretty awesome, right? So there's a magic keyword which we need to use here, and the keyword is reflection. C# will give us access to all the relevant information of the source code to write a generic serializer. We can then pass any function, any struct or class into that function and get a JSON string back without having to write any code. And this is pretty freaking awesome. We cannot just use that for writing serializers. We can also use it to maybe drive our UI. So we can have a class user, and we want to build in our UI. We can just say, like, all right, the ID is an integer field. The name is a string field or a text field. And then we have a list of strings. Let's have a quick look how we do that in C#. C# has a magic function which is attached to every single class in the program, even int and float, and it's called getType. We can use getType to get access to the runtime type of the set variable. So as you can see here, we have the user variable, which we created before, and we call getType on it. GetType will return a type T in this case. And type is a runtime type. This is different to the types we have in C++ today. Today, if we want to work with types, we do that usually via templates. And templates are completely restricted to compile time. We cannot use them at runtime. It's impossible. So let's have a look at the type class and take a quick look at the documentation. That's an excerpt of the documentation. You're not supposed to read that, actually. It's just a lot of stuff is on there. And we can do a lot of things. There's two methods which are of interest for us today. And those are called getFields and getMethods. They pretty much do what they say. You get access to all the fields of the class, and you get access to all the methods of the class. Now we need to take a look at how we can actually use that. So here's a quick example, which is still using the user variable which we created before. We will get the type by calling getType on it. Then we will get all the fields, put them in a field info variable, and then we just iterate over them. We iterate over all the variables and just print some information about them. In this case, we print the name and the type. If you now look at the console, we see that. And this is the representation of the program, of the struct, available at runtime. So this is pretty darn cool. However, this is CppCon, not CSharpCon. So we got to go back to C++. And we just take that program, and we translate it into C++. This is the more or less exact replica of said program in C#. We replaced the getType function, which was a member function on the class, into a template called getClass. Because it kind of makes sense to, like, if you want to get access information about a class, we call a function not getClass, not getType. Then we replicate the loop. We loop with a for-range loop, which is super awesome, over all the fields, and we print the information about the fields. And we take this function as sort of like a blueprint. This program, as a sort of a blueprint. And we will now try to come up with an API which is able to provide us this information to build this simple program. Because if we have this simple program, we can write the more complicated serializers with just the information. So we start at the bottom. We start by defining a type. Because if you remember correctly, in C++, everything starts with primitive types. So you have, for example, an int or a float, and then you make a struct out of ints or floats, and you make a struct out of structs, and so on and so forth. So we start with type. If you think about it, what Herb Sutter said earlier today in the keynote, a type is basically two things. It's a name and it's a size. Here we just represent those as two variables on the struct. Size is basically the equivalent of size of a t at compile time, just available at runtime. And the name is pretty much the equivalent to the C++ type. So for the case of an int, it would say int. Next, we define classes. And classes just are types as well. So we inherit from the other type we just defined, and we add some more members. A class, different to a primitive type, like int, has fields or functions. So we just add a variable for fields and a variable for functions. So I kept it simple here. Technically, we could also add like constructors, but for the sake of simplicity, I kept that out here. Now we have two more classes we need to define. As you can see here, we have field and function. So let's define them real quick. We start with field, because it's more obvious. And the field itself has a type. So we just put a type pointer in there, has a name, and an offset. So you might ask, why offset? Offset is important because we can use the offset to later get access to this variable at runtime. So if you have, for example, a pointer to the struct of user, and you want to get the name, you have to go to the offset of the name variable, and cast it to a string, and then get the string out of that. And this is something we will have to do later, but we will obviously automate that because casting to some random type is obviously dangerous. Next, we will continue with a function. A function is basically made out of a return value, some sort of parameters, 0 to n, and a name. We use fields to represent return values and function and parameters here. This is not exactly 100% correct, but it's a good enough approximation here. With that, we have a single slide with all of our API. With just this information in our program, we can already build the example we had from before. I have omitted the convenient accessors and mutators for convenience here to put it actually on the slide. This is just the data members. So this leaves us with a question. We have this API now. How do we get the data out of that? Because it's just an API. It doesn't matter too much to us. We cannot create those types at runtime, but that would mean we create it by hand. Actually, let's do that real quick, because it's kind of nice to just create it by hand and test it out. So just as a remember, this is the class we were talking about, or struct here, the user. So now we need to implement a way to get access to the information of that user, or of that struct. And we do that, if we imagine our example back, with the getClass function. And we apply the very same techniques here. We just create an overload of getClass. It's pretty simple. So here we have the overload. It's getClass, specialized for user. We create a static class. We add the first member variable, which is called ID. Then we create a second member variable. We create the third member variable. And we return it from the class. It's a simple static variable returned by pointer. It's perfectly fine. Let's compile that. Oh, we got a link error. What's happening here? We've called a function called getType. So if you remember, as you can see, there's, if you go back, there's here, the first line is getType of uint64. But we have never defined getType. And uint64 is a built-in type, so it's a primitive or fundamental type. That means we need to define the fundamental types of the C++ language before we can actually do something useful here. That will also mean we actually need to write some code by hand. This is unfortunate, but it's required. We only need to define these 15 different types, which is like long, int, unsigned long, and so forth, and so on and so forth. So let's go back to the compiler error, and we get back here. This is the, well, perfect. So we need to define the primitive types. So why did I put that in quotes? It's in quotes because we need to cheat a little bit here. And excuse me for that, because std_string is actually not a primitive type, if you know that. And so is std_vector. But for our intents and purposes, defining std_string and std_vector is a very good approximation of a primitive type, because std_string and std_vector are both classes, but behave very differently. They are data structures. If you would print out all the members of a std_string or a std_vector, you wouldn't get what you expect, because you print out a pointer to char and some size and some length, and some size and some capacity if you print the string to JSON. That's not very useful. So we need to have a way to say, all right, this is std_string, this is a zero-terminated string, and we need to print out everything until it's 0. So we need to write some code here. This is just, this is a definition of getType for int. And this is everything we need to do. We do that now for every primitive type we have. We just add the name and do size off. We can actually automate that with some macros, but I omitted that here. So if you paid attention, or rather paid very good attention to the compiler error, you saw that there was a compiler error regarding std_vector of std_string. And you also saw that we used the getClass function which was templated on std_vector of t to get a std_vector of std_string. This is something which actually doesn't work. So we need to have one more level of inherit, or one more level of abstraction here. And we need to use type dispatch to actually get reflection data of a templated type. So this is implementing the get type for std vector of t. We can use that to get access of std vector of string, std vector of int, std vector of pretty much any type. And this is pretty damn cool. So let's go back to implementing the real get class. And this will also use tag dispatch just to keep everything in sync. So the same thing, we create a static class. We then add the fields. The first field is here, that's ID. We give it a type and an offset. We then do the same for name and the same for pets. Return it. And that is pretty much it. This is the whole implementation of get class. With that, we can now go back to our example and print all the fields. So we do the same thing as we did before. We call get class, we get the class, and we iterate over all the fields. And this will work. This does work. But we still have to write code by hand. And we don't like writing code by hand for something like that. So we need some way to manually, to automatically generate the code we need. And for that, LLVM comes into play. So show of hands, who has heard of LLVM before? Good, pretty much everybody. Who has used LLVM before? That's a sizable amount of people. I didn't expect that. That's pretty good. So I didn't need to fill you in on all the information probably, but quickly. LLVM is a compiler framework. It's basically a set of libraries to build compilers with. It was created in 2003 by Chris Latner for his master's thesis. And it's the main backend for the Clang compiler, which is the main toolchain for macOS and Chrome, for example. But we cannot do that with just Clang, with just LLVM. We need to use Clang as well, because LLVM is the low-level part of that, but we need to parse actual C++. And there's a nice library, which is basically inside Clang, and it's called libtooling. Libtooling will give us access to the complete AST of a parsed C++ source file, or a program, rather. And if you don't know what an AST is the abstract syntax tree, so it's a tree data structure of your source code. You can use that to introspect the whole source code and extract information. And this information we will use to generate C++ source code, which we will then later include in our programs and will include the required reflection information. So how do we do that? And I mentioned that before, because I gave away the point of that slide, is we just generate some C++ source code. We could use more advanced techniques here to maybe generate an object file or generate a database, but we just opted in for the very easy one. We generate some source code, we include that in our programs, and that will include the information we need. So let's get started. I'm assuming here we set up all the libtooling stuff, we set up all the LLVM compiler stuff, the rather boring stuff, and we start writing code. And if you do that first, you probably want to do a quick way to check if everything works. So you go ahead and just do the hello world of it, which is basically running over the whole program and printing the AST out to the command line, to the console. This is the hello world. You don't actually need to read that. It's just really going over the whole program and printing out the AST. So here we have a program which you want to analyze or rather run through the AST dumper. It has the normal includes we need, and it has the struct. Let's have a look at the results we get back from our little example. Yeah, it's 106,000 lines of AST. I couldn't fit that on the slide. I tried, but pretty much every program I tried to paste that in crashed on me. We can take a deeper look at that, and I did that real quick. It contains over 2,000 records, which is every struct and class. And those have over 1,000 fields. So if you now would generate all the reflection information of all the structs in that simple program, you would generate a huge amount of information. And it is obviously something we don't want to do. So we need to have a better plan here. We need to have a way to filter exactly, or to select exactly the class and fields we want to reflect. And there's a couple ways here, but the easiest way to do is just to annotate every single class we have and want to have reflected in every single field with an attribute. Because C++ has these awesome square bracket attributes. Unfortunately, though, we need to use an attribute which is catchable inside Clang, which means it needs to be defined. My first idea was here to just use square brackets, reflect. Because the C++ compiler has to, or can ignore, should ignore, unknown attributes. However, since the attribute is unknown, there's no way to actually query for it via AST visitors, or AST matches, rather. So I opted in to do that via the annotate attribute. And here's the code for that. Kind of a mouthful, right? So we do the usual thing, and we turn everything which is large into macros. We have some nice macros which will just make this easier for us. Now we have to just attach the class macro to every single class, and the property macro to every single field we want to have reflected. This will allow us to go into the lib tooling, use something called an AST matcher, and we'll then just match exactly every AST node we want to have. So let's do that real quick. Here we have a match finder and a class finder. The class finder is a class I will come back later. It's something we have to define. And the match finder is something which is defined by LLVM. We then create all the AST matches we need. As you can see here, we have 3 matchers. We need to match for CXX records, which are structs and classes. We need to match for fields, and we need to match for functions, because those are the 3 primitives I've chosen here to reflect. And then we need to filter them. You can see there at the end of every line, there's a little function call, has attr, has attribute. That means it will only match the attribute, the CXX records or functions which have the annotate attribute. Then we just add them to the finder, and we call our tool. If we now run the tool, we get exactly all the nodes we want. Then as a start, we just do the same thing as we did before and dump them to the command line. But before we do that, we need to get a way to actually get access to them. And this is where the class finder comes in play. The class finder is just an interface, or inherits from the interface of match callback, which has 3 functions we need to define. The bottom 2 functions are rather self-descriptive, on end of translation unit and on begin of translation unit. They'll be called when the translation unit starts and the translation unit ends. The run function is the interesting function here. Run is called for every single match of our finders. So for every single CXX record, for every single function, and for every single field. So now we need to define the run function. The run function can be kept rather simple. We get an information object here back, and the result object, we have pretty much only like 2 functions to call, and one of them is getNodeAs. GetNodeAs is basically the LLVM equivalent, I think, to dynamic cast. So we just try if the node is a CXX record. If the node is a CXX record, then we just keep it around. In that case, found record, we'll just dump it. The same thing for the fields, and the same thing for the functions. Once we've done that, we can take a quick look at the implementations of those 3 functions, and they will just dump the node to the standard out. So now we can have a look at running the program over our previously defined little snippet of code, which has all the includes and printed us previously 106,000 lines of AST. Now it's down to this. This is all we have, and this is pretty awesome. You don't have to read that. It's just saying it's a struct, it's 3 member variables, and that's it. There's some information on that regarding whether there's a constructor and what's the name of it, what's the type of it, and all of this information comes in handy. Because we'll use this information to generate our C++ source code, which will contain all the reflection information in the end. So now we need to do the actual generation. Or rather, we need to keep around the nodes, because previously in found record and found function and found field, we just dumped them. So we just create a simple class called class, and we will add the fields and the functions. We will assume here that since C++ source code is rather from the top to the bottom, that once a class starts, every function and field which will come after that class belongs to that class. And if a new class starts, we start a new class, and we put the functions and fields of that class onto that class again. This is really simple. If you look at the add field and add function there, it's just pushing everything back into a vector. So we now have every function and every field attached to a class. That's pretty cool. We can use that, and we will do that. But first, we need to figure out when we actually end our parsing, because we just parse everything, and we need to wait to have everything. And that is done in the on-end of translation unit function. Once we reach the end, we loop through all the classes we've previously generated, or we've previously captured, and we'll generate the code for that. Now, slowly and steadily, the pieces of the puzzle will come together. We will now have all the structs, all the fields, and all the functions of that struct in our class, and we can now use that information to generate some code. Finally, half an hour in. So, code generation. As I've said before, it will just generate the code by printing out everything we need, by looking at the AST nodes and then printing out the C++ source code. This source code can be then put into a header, and this header can then be included into the translation unit of your program. So you can imagine that you have class.h, class.cpp. Class.h will have the nice property and nice class macros. You run the reflection over that, and then it will generate you class.generated.h. This you can simply include in the class.cpp, and will contain your information. So let's dive a little bit into the Clang AST. Here we have the generate function of our class, of a reflected class, and it's basically just printing all the things we need. So what we have here is some setup stuff, which I've just dotted out here because we're just printing like pragma1s, the namespace, the header guards, and stuff like that. Then we will create the overload of the function we've seen before, or rather implemented before, the get class impl, which will just create an overload or create a template specialization of the class user. So once we've done that, we can iterate over all the fields, iterate over all the functions, and generate the code for all fields and for all functions. So with that in mind, we take a look at the field generator. The field generator is reasonably simple because if we're honest, the information we actually have is just like 3 member variables. So we take a look here. We generate the field. We generate information for each of the fields. This is generating information for a single field. That is why we pass in the size ti, which is the index of the field. And then we generate the type, which is actually supposed to be a get type function call. Then we put in the name and the offset of. And with that, we can actually generate all the information we need. And this is pretty much everything we need. And now I'm going to quickly show you that. And I need to make it a lot bigger, I guess. And I need to mirror it. All right. Can you see that? Can you read that? Like that. Perfect. So, what we have here Why is that here? Anyway, what we have here is our user class. This is the same class we had before. User with an ID, with a name, and the strings, vector string, which is called pets. Very same thing. So then we have the main function here, the main class here. Why is that in this different state I mentioned it to be in? So here we have the same creation of our user. It's just the user. We set the ID to 42. We give him a name, and we give him his two cute dogs, Buddy and Cooper. So this is the dump function, which will do the JSON generation. Look here, and make run. You see a lot of stuff happening. And we see the JSON generated. At the bottom here. This is the same JSON, just without the actual formatting, which we had before. As you can see here, ID is 42, name is John, pets, Buddy and Cooper. The dump function as well does a debug dump. So this is one of the nice uses of reflection as well. So you have like something you want to visualize in your debugging builds, and you have a struct, and you want to print it out. Nowadays, you need to write an overload of operator left shift. But with reflection, this is a thing of the past. You can just user, and then print it out via the dump, and you get all the information you need. And you can see that right here. This is doing the very same thing, just a little more verbose than the JSON output. It's using the same information, and it will give you a nice, very awesome overview of what the representation of a class is, if you want to look at it, to debug. It's pretty much the same thing as you can do in Visual Studio, GDB, LLVM, and all the other debuggers, with one difference, and that it is available at runtime all the time. You can disable that debug if you want to reduce the executable size a little bit, but generally, this is something which you might want to do. So this implementation here will be available on GitHub, and there's 2 versions of that, because there's a story attached to that. The talk title was writing a reflection template in 1 weekend. So that's why there's 2 versions. There's the 1 weekend version, which is on the master branch, and there's the developed version, which is that. You can take a look at the 1 weekend version. It's a little less polished as this one, but it will give you a nice overview over the project. So let's go back to talk. All right, so with that in mind, we can take a look at the future. This is great, but it's a little similar to what we have already in C++. And in that, it's creating overhead we might not want or we might not like. It's a little similar to type ID. And Arvid mentioned that earlier today as well. Type ID is regularly disabled in programs because type ID creates information to be available at runtime which you might not use. The same thing applies here, unfortunately. But since we can actually select only the things we want to inspect, we can filter out everything we don't need. However, we can improve upon that. We can, for example, generate an object file instead and link that in, so that removes the step of compiling everything twice. So we can just take LLVM, take the source code we've generated, run that at build time, and then link that in. If we don't want to have the information in our program itself, we can also create a database, like a program database, like a PDB, call it RDB, reflection database. We can then load the database at runtime and load only the information we want to have. So we can have a runtime database which can be multiple megabytes large and a smallish executable, and then load only the information we actually need at runtime. We can further compress the information in the database, for example. We can also compress the information in our program itself. We want to embed that via something like std_embed, which will come later. Or we can call it to DLL. There's many different ways to do that. So this is only the start. This is a very simple way. to do that. So this is the main part. I've got a few bonus slides to give you a little bit more information about the actual implementation of that. Because if you notice that, I've cut a couple corners here and there to make it a little simpler to present. If you remember the very early slides, we saw on the class struct that functions and fields were arrays of n. But I never got around to actually define what n is. We could use n and make n just something largest and assume we never have a function which has more than 32 or 64 or 128 functions or fields. This is not exactly too good, right? So in the actual implementation, we have something called a class storage. And this is the actual definition of the class in the actual project. We only get 2 pointers, which is basically 2 iterators. The beginning of the fields, the ending of the fields, the begin of the function, and the end of the function. Then we will create the data in an external class. So all the data lives externally. This prevents us from, or this will allow us to not templatize the class itself, and we can pass it around as a normal pointer or reference. So here in the end, so here we have the actual implementation of the class storage. The class storage is actually templatized, so we can say, all right, this class has 3 fields, 0 functions, and is of type user. We'll then create an array of 3 fields and 1 function, because arrays of 0 are undefined behavior. And we'll just pass the first pointer and the last pointer into the class. This allows us to do one thing, which is really important to do if you want to embed information, and that is avoids dynamic allocations. The easy way would just to use a set vector, and then just set vector of point, and then just push everything back into the vector. But that would create a dynamic memory allocation every single time we actually look at the implementation. We look at the reflection data, and we obviously want to avoid that. And here we have the LLVM setup, which you can later look up when you look at the slides. And here's one thing, which is pretty nice, and that is the actual annotation setup we have in the actual project. I'm using that in production, and I'm using that to attach properties onto functions or fields. That means we can say what you've seen in the source code, like we have a class and we have X amount of fields, but we only serialize a couple of those. So we say property, parentheses, serialize, parentheses. That means we only serialize what we actually want to serialize. And we can pretty much extend this bare-bone project with everything we want in the end. We could say, all right, this is a function, and we want to replicate that function over the network. Or this is a property, it's a string, but please treat it as a string. Or whatever your heart desire. One of the common uses is to inject other code. So you could, for example, generate a setter or a getter. This will kind of go into the detail of what meta classes can do as well, but it's out of the scope of that talk. So I finished on time. Thank you very much. Yep, here's the links. Any questions? Yes.
Okay, in here you're talking about reflection for the fields. Do you have any in mind, like if you're using like a reflection to get the function names and then you want to invoke it on the runtime by calling the specific function name like that? Do you have anything?
Yes, the question was whether I have access to the functions and can call the function as well. Yes, the actual final project you'll find on GitHub can do that. You have access to all the functions. You can get them by name, and you can call them. The calling part is rather complicated. It requires a little bit of trickery, but it's possible. All right.
How do you support raw pointer? Like for string and vector, it store data. Actually, there is a raw pointer to point to the data.
Ah. Yeah. So the question is how I support strings and how I support vectors, because it's a pointer to a raw pointer. It's a pointer to the elements. Yes. String can be supported by using the annotations. You can say like string, and then you basically create custom behavior for that. But I opted for the way to specialize for std string. I can show you that real quick. In the source code, we have the implementation for primitives. Called fundamentals here, which you can see, no, template. So here we have std string. This is the get class implementation of std string. Std string creates something called a string class, which inherits from our class and has some custom behavior attached. Because as you said, yes, containers are very different to what our normal reflection would do. If you would normally just reflect a chart pointer, we would probably just print the value of the pointer. But in a string context, this doesn't make any sense. And especially for a vector, it doesn't make even less sense because you want to go through all the elements of the vector and you want to print all the information about the vector, about the elements in the vector, and not just where the vector actually points, because the memory is not of interest. The elements are of interest.
Okay, so there should be special code for vector as well.
Yes, there is special code for vector as well.
Okay.
If you look here, we have get class simple of vector. And this is actually the reason why we had to use a tag dispatch. Because std vector, as we all know, is a template. And this needs to be available at compile time to the compiler to create reflection data for every vector of t. And we also have the custom behavior for the visit here, which will start an array, as you can see here. We'll start an array, we will end an array, and we will visit either all the elements or we'll just print the primitive. Thank you.
Hi, nice talk. I was wondering if this work with inheritance.
Pardon me?
If there is inheritance on user structure.
Oh, the question is whether there's inheritance.
Yes.
So you want to get access to the, for example, the base class of the user.
For example.
Yes, you can do that. I haven't implemented that yet, but it's absolutely possible.
Hi. Do you find any challenges in debugging the generated code
Pardon me?
for the LVM?
Come again?
The challenges, any challenges in debugging the generated code?
Oh, the generated code, the question was whether there are any challenges in debugging the generated code. The generated code is pretty simple. I can actually show you the real code here. And we have the reflected class here. And this is pretty much just printing out everything into a string stream, the same way you would write the code. My process actually was, when I was writing that, and actually I wrote the initial implementation in one weekend, was to just write the real implementation once, come up with the API, write the real implementation, and then re-implement this API in the compiler, in the libclang, libtooling, and do the very same thing. This allowed me to first come up with the design of it, and then do the actual implementation in LLVM, because it's a lot easier.
Okay, thank you.
You're welcome.
Does it take into account any kind of versioning or anything like that? Do you worry about that at all for your particular problem space?
For my particular problem space, I don't worry about versioning, but I do worry about the types. If you've seen the output here, oops, the JSON has an __ type attached, which is a large number. This is actually the hash of the type name. This allows me, when I'm unserializing something, that I can verify that I'm unserializing it in the correct type. So if I would now, for example, this is the user. We have the user here. We would serialize the JSON to disk, stop the program, start up the program again, and try to unserialize it. If we now would try to unserialize the user into a different struct like train, we would obviously get not the information we want to get. So this makes sure that we check at runtime whether the type of the JSON matches the type which we passed in. So this will make sure that the types match. But there's no versioning yet attached. But this shouldn't be too hard because we can make use of the annotations we've seen before. With the annotation, we can just say version equals 1.1 or 1.0 and emit that.
Thank you.
You're welcome.
If you had a base class pointer which pointed to a derived class,
Yes.
how would it work?
So the question is how it would work if we have a base class pointer to derived class pointer, right? Since we have so the one thing I think you're missing here is that we need to get the type information or the reflection information via the get class function. Get class is a template. That means if we try to get information from if you pass in a derived class pointer and get information about the base class, you will only get all the information in the base class. This will omit all the information in the derived class. This is different than type ID. With type ID, we have the information attached to the user pointer in the v table and can get access via a base class pointer to the information of the derived class if you initialize as a derived class. So this will not work in this case.
Okay,
Thank you. All right, thank you very much.